we have Brian Blum. He's from Langan. Is that right?
That's right.
And Brian is going to give you kind of an introduction to what geothermal energy is and some of the promise that can be tapped from the ground. All right. So Brian, take it away.
Hi, good morning. Thanks for having me here. So I will talk about geothermal systems, and I'm going to talk about them from the perspective of a geologist, okay? Does anyone know what I'm talking about when I say a geothermal system? Anyone have an idea? All right, no one wants to volunteer. Okay. I want to try to make it a little interactive, so I'm going to call out on you guys, so pay attention. So this presentation is actually developed for professional architects. And architects have to get professional development hours to keep up with their field, and as a result they attend lectures, and this lecture was developed for architects in mind. And so the presentation overview is, first off, there's learning objectives, and as students I hope that you come away with understanding a little about geothermal systems. I'll talk about the basics of these systems, the types of systems that are being built, the types of ground couple, how geology comes to play, feasibility studies, which is a study to determine whether or not it's feasible at your building or at your site, wherever you may want to use a geothermal system. And then finally I'll get into some field testing, actual construction projects, and then lessons learned from a project we did for Columbia University. So what's a geothermal heating and cooling system? So a lot of you may have heard about geothermal. Geothermal is often used to generate electricity. That's in an area where you have a geologically unstable environment, like Iceland, the western United States, and I'm not talking about that at all. So if what you think about geothermal is a means of generating electricity through the Earth's core temperature, that's not what I'm talking about. Here I'm talking about what's called low temperature geothermal. It's basically using the average Earth temperature as a couple to either gain heat or reject heat, okay? I'll talk about the systems that are being built in the Northeast, whether or not it's practical for any application. Again, this is from an architect's perspective, whether or not it's practical for their sites. How does a geologist get involved? Are any of you geology students or environmental students here? All right. So, and ultimately, what we look at is geothermal right for your site? Is it right for any given building application? So I love teaching rules of thumb, so hopefully there are simple things you can get out of this. Here's a little fact. So you have a map in front of you of the United States, and generally in geologic stable areas, which what we have here in New Jersey and throughout the Northeast, we don't have volcanoes, we don't have earthquakes, not much of them anyway. We have pretty stable ground, and more or less the average Earth temperature is equal to the average ambient air temperature. So what does that mean? If I give an example, if I drill a hole in the ground deeper than about 20 feet and no deeper than about 2,000 feet, so between about 20 and 2,000 feet in Philadelphia, or if I did it in New Jersey, whatever, I would basically pretty much guarantee that the Earth temperature at that point is 53 degrees. And that's equal to the mean average annual air temperature in Philadelphia. Okay? So that's the whole basis on how geothermal systems work, is that you're taking advantage of a consistent Earth temperature to either reject heat in the summer or draw heat out in the winter. So you could imagine if it's 95 degrees out, it's nice to start with 53 degrees as a means to cool your building. And if it's 20 degrees out, it's nice to have 53 degrees as a means to heat your building. Okay, so that's all it is using the Earth's basic temperature as a means to either reject heat or take heat. What you see on the left is just a diagram of the Earth. And what I want to represent there is these systems really just go to the onion skin of the Earth, if you will. We're just tapping 2,000 feet at deepest, and often much less, is just nothing compared to the overall extent of the Earth. So it's not like we're drilling down to the core of the Earth, if you will, okay? We're drilling relatively shallow holes. And on the right, there's a graph there. And I know you can't read it from there, but basically what it's saying is that the Earth temperature does fluctuate at shallow depths. So we all know you have to be about beneath 3 or 4 feet to avoid frost line. So we put these systems in at depth. Greater than 20 feet on that graph, it's showing you that the Earth temperature doesn't fluctuate. So that's why I mentioned if I drill deeper than 20 feet and shallower than 2,000 feet, I more or less have that constant temperature. And in New Jersey, it's in the 50s. So why is geothermal considered? What are its advantages, its disadvantages? So this is one slide that I borrowed from a mechanical engineer, who, by the way, mechanical engineers are the folks that are involved with designing HVAC systems. They're the ones that are designing the heating and the cooling systems for a building. Just like this building, an engineer had to come up with a design for all these vents and to deliver air that will either cool or heat this building, okay? So what I want to represent here is that this example has a schoolhouse on the upper right-hand side, and if you purchase 1 unit of electricity and you use that electricity to run a geothermal heat pump, the heat pump is connected to the Earth, and with that you're getting 3 free units of heat to deliver 4 units of heat to the school. So when you look at a slide like this, you say, wow, if there's free energy to be gained from the Earth, how come we just don't have geothermal systems all over the place? Why aren't they not just a given for any building that's ever built? And the reason being is because in order to get these 3 units of free energy, you have to have a lot of factors that coincidentally come to play in order to make it economically worthwhile. Because to get these 3 units of free energy, you have to spend a lot of money to do it in order to couple to the Earth and exchange heat with the Earth. And the only way that money could get paid back is if your site has some advantages to it, and that over time, the expense that you put in up front, that capital expense, pays off for itself in a reasonable time. And typically what's reasonable, if it's less than 10 years, people want to look at it. If it's 10 to 15 years, it's a borderline. It depends on what the building is being used for. And if it's greater than 15 years, nobody wants to invest that money. No one wants to find out, like, I'll save money 15 years from now if I build a geothermal system. That's when it will start paying back, because people don't know where they're going to be for 15 years. Okay? So it's a very important basis of this whole geothermal exercise, is making a determination, and this is what engineers do, is determine whether or not it's worthwhile economically to invest to get those free units of heat or cooling when you put a geothermal system in. So the rest of my discussion is going to focus on the types of systems, and then based on those types of systems, is it worthwhile? All right? By the way, as I'm going through this, if you have any questions, speak up and ask. So a lot of times folks are interested in putting geothermal systems in because they want to build a energy efficient building. They want it to be green. And what this slide is about is that, I speak to architects when I give this presentation, and what I try to tell architects is the most important part of being green or saving energy is really how the building is constructed, what materials are used, how we call it the skin of the building. Is it efficient? Is it efficient in keeping the building cooled or heated to the extent that you do that? So that's very important. I have a little table on the left side that tells me, as a rule of thumb, when someone's considering a building, what type of energy load is needed. And when I say energy load, there's an expression called tons. And just like horsepower tells you how powerful an engine is for a car, tons tells you the capacity of a heating and cooling system. And it's from an old expression of what cooling is derived from a 1-ton block of ice melting. Okay, so that's where that expression comes from. But mechanical engineers design cooling systems, and the sizing of those systems is in tons. So this building is cooled, and there's a cooling system that has basically a ton capacity to it, as determined by an engineer and also architect based on the use of the building and how it's put together. So this is probably my most important slide. I'll spend more time on this slide of any other slide, and I'd say if you're paying attention, here's where to pay attention the most, okay? I'm going to go from right to left and the bottom to the top. These are by far the most common types of geothermal systems. And again, what I'm talking about is how the coupling is made with the ground to exchange heat with the earth, all right? So the most common type by far is called a closed loop system. And I think, could everyone see that from here? I hope so. So a closed loop system is basically a drilled bore into the ground. Conventionally, it's done somewhere in the neighborhood of 150 to 500 feet. It's dependent on the geology, the geologic conditions. It depends on permitting. In New York State, if I want to drill deeper than 500 feet, I need a permit. So if I'm going to drill this type of well in New York, I would say don't go deeper than 500 feet. We don't need to get a permit. Permits are expensive. And we want to minimize the capital cost of installing these systems. So let's say 500-foot bore is put into the ground, and then the driller who drills this bore inserts a plastic tube that's basically shaped like a U into the ground, and liquid and water and an antifreeze mixture, which has about the consistency of vodka, goes and circulates through the tube into a heat pump where, again, heat is either rejected or taken from the ground. And it's basically that contact with the earth where that heat exchange happens. These are basically, for a 500-footer, you get about 2.5 tons of cooling capacity, and they have to be put on centers of about 15 to 20 feet apart. So to give you a perspective, what does that mean? If I put in a building with 250-ton capacity, which is a nice sized building, maybe, I don't know the size of this building, but let's say it's something like a building this size, it would mean I need 100 boreholes somewhere out there in the environment and tied into this building, okay? When people put in homes, they're putting in maybe 3 of those type of holes or 2 of those holes. They're the most efficient because, they're not the most efficient, they're most trustworthy because there's no mechanical devices that are put in the ground, and once they're installed, they can be covered with an athletic field, with a building, with parking areas, with roadways, you name it. The second type of system is called an open loop system. It's by far the most efficient system, but it's not as trustworthy. It's efficient in that it exchanges heat in the best way because you're directly pumping groundwater out of the ground and using the groundwater as a means of exchanging heat as opposed to going through plastic pipes to exchange heat. The groundwater is built like a conventional water supply well, and basically for every ton you need 1.5 gallons of water, and the water comes out of the ground and circulates back into the ground. Now the problem is when water is in the ground, it's at a basic temperature that's in equilibrium with the earth. And the example I gave, it's let's say in the 50-degree range. Groundwater has natural minerals in it, and there's a chemistry equilibrium in the ground. When you pump that water up and you change the heat of the water, or change the temperature, excuse me, you're creating a disequilibrium with those minerals and chemicals that are in the groundwater. And when you put the water back into the ground at a different temperature, that creates a problem in putting the water back in the ground, because you tend to have things like scaling. You have precipitates forming, like calcium and iron and manganese, natural metals that are in the earth. And you've now taken them out of their comfort zone, which was whatever equilibrium condition they were at that temperature, and you've changed it by putting it back in the ground. And so, in theory, for every one well you need to take water out of the ground, all you need is a mirror image of that well to put water in the ground. But in practice, you need at least 2 for 1, sometimes 3 for 1. So working with water is the best way of exchanging heat with the earth, but it's also a chemical challenge and a mechanical challenge, because you also have a pump that's in the ground. And you're basically, now you have a component of your heating and cooling system for a building that's not in the building. And conventionally, engineers who design buildings, they don't like that. They want everything in the building. And the person working on repairing or making changes to the system wants to work in the building. And also you have to have constant access to that well. So unlike these, which could be buried and put under the athletic field, these you have to have constant access to. And by access, I mean a vehicle the size of a hook and ladder fire truck has to be able to park over those wells and possibly do some maintenance and repair. And that could be challenging in certain urban or suburban environments. The third system is called a standing column well. And it's a hybrid of the two. It's similar to the closed loop and similar to the open loop in certain ways. And basically, this is what's being put in mostly in your core urban areas. So if someone was considering a geothermal system in Newark, New Jersey, or New York City, these are the types of wells that are being put in. How they're hybrid, and I'll get in more into these, is that they basically are a one point, similar to the closed loop, where heat exchange is circulated in and out of that one borehole, even though we have several of them manifolded. But it's like an open loop that you still are directly exchanging groundwater, and there's a pump in the well. In this case, you have a 1,500-foot hole. You have, inside that borehole, there's a casing and a screen. The screen allows water. It's almost like having a straw in the ground with holes on the bottom of the straw to allow water to get in. The water is pumped up, brought up by the pump, goes out to a heat exchange, and then comes back in and is circulating all the way down to reach an equilibrium to exchange heat again. So these are the most common types of earth couples, but there's many other ways to do it. These are the most common types in the Northeast, where land is a challenge. We don't have a lot of real estate. There are other systems. Cornell University has one of the most efficient heat exchange systems, and they exchange heat directly with one of the Finger Lakes of New York, Cayuga Lake. And their coefficient of performance is 20. So they're getting like 20 units of free energy for every unit they purchase. But we don't always have an enormous lake next to us that is of great depth to do those types of things. Any questions? All right, easy crowd. So now I'm going to just go through these systems so you get to learn them a little better. I'll show you some pictures, and hopefully the pictures will get you thinking about these things. So this is just what a cartoon rendering, if you will, of what a closed loop system is. Here you have, let's say, an office building, a suburban park office building. And you typically, in a suburban park office building, you have vegetated areas and parking areas. Pretty boring, but that's basically what you have. And here you have these closed loop wells that are manifolded together, and they're brought into the building. Now what goes on in the building? That's the engineering part, that's the mechanical engineering part. And for the most part, the difference is instead of having a conventional boiler or a conventional exchange system for air conditioning, a water to air or an air to air exchange, you just have a geothermal heat pump. So architects look at it and there's one advantage of going with a geothermal for them, and that is because they're exchanging heat with the ground and they're running it electronically, there's no need to exhaust any hydrocarbons. So you don't have a gas boiler, you don't have an oil boiler, there's no reason to have a chimney or a flue to exhaust. So, but other than that, for the most part, the architect looks at it and says, I still need a mechanical room to put my pump, and that mechanical room is in the same place that a boiler would have gone. So really inside the building, not a big change in how the building mechanical system looks. It's really all about this. This is the most unique part to a geothermal system, and that's why a geologist is standing up in front of you talking about it, because mechanical engineers, they know everything in the building, all the design system, all this duct and piping, but they don't really get into designing an exchange system with the earth. It's not what they're trained at.
Yeah. Now, and correct me on this, but is it also something where you have to keep the building itself in a closed system? You don't want to have windows open and stuff because you're going to have the loss of heat and such? Because I understand that another university put in one of these and they didn't calculate for the acid goods and other things, so their system wasn't as efficient as they thought it was going to be.
Right. That's a good question. I will say it's out of my field in terms of that is now back in the realm of the architect and the mechanical engineer. But certainly what we know is that there is gained efficiency by engineering your building so that there are the least amount of variables possible. But that said, we know that while it may be just completely more efficient to have windows that don't open and such, people still like opening windows. So, you know, there's a yin and yang to that. So, and that's something that's certainly challenging. Now, in a commercial setting, there's code and zoning rules that just say, no, this is the way it's going to be done. Your windows are not going to be open because of that potential loss. But obviously, in a residential setting, you're going to probably still have designed buildings with windows that could open because people just like opening the you know, on a nice, hopefully we'll have some nice April days where it's 70 degrees and people will want to open their windows. So these systems, they do get built residentially and for small buildings, not just large universities. And by the way, like, that's where these systems are being built today. They're being built in a lot of municipal buildings. They're being built in high schools and colleges. And the reason being, and I talked about the economics, when a private developer is building, they look at their economics as not just the cost or extra cost of investment. They look at it, is there money going to come back to them? And you know, a developer may buy and purchase ground, and they may build something like a strip mall or a shopping center. And then after about 3 years, they may decide to sell that shopping center and to a management company that may just manages the shopping center and collects rent and so on. And there's no advantage to them in spending that extra money because they're not going to get it back. And the manager of the shopping center is still they're going to basically get tenants to come in, and they may say to their tenants, we could save you money. We have a geothermal system, but we want more rent. And people will say, no, I don't want to do that. So it's commercially challenging to get these systems in. So it's usually by owners that are going to be around. So a school district builds a high school and they're going to be around. And they know that they're going to be spending money to heat and cool that high school for years and years to come. So they look at it with a perspective of long-time ownership, as does a university, as does a municipal courthouse, a police station, a fire station. we see them being built in those types of environments, or a private owner. Yeah, question?
We see a lot of buildings nowadays get renovated, or older buildings that get demolished and kind of rebuilt. With this sort of system for geothermal, is there the ability for if a building gets renovated, or if it gets, say, they still have the system there, but it gets demoed, are they able to keep that in place and then just put that towards the new renovation of the new building, or would that have to be adjusted or reinstall a new system?
That's a great question. So if you have a building, so we talked about the type of sizing of the building, okay? So simply put, if you have a building with a geothermal system, and now I will say your example is not something that's out there yet, because these systems are relatively new. So someone putting in a geothermal system in the last 10 years is probably not knocking down their building. But 15, 20 years from now, if they decide to, they would look at it and say, we have a closed loop system and it's capable of delivering 100 tons. What's our new building going to be like? The system out there is okay. It doesn't need to be changed. If you're going to replace it with 100 tons or less, if you're going to go with more than 100 tons, then you have to consider that. So certainly that's a consideration. Does that answer your question?
Yeah, and are they able to, like, especially with like closed loop stuff, are they able to add additional, like, I guess, boreholes into the system?
Yes.
Okay.
Yes. Now, closed loop is, again, a little more user-friendly once it's installed. If you have wells, then you have something that's, I say that a well that is an open loop system is like a living and breathing thing. It's something that constantly needs maintenance and care, and if you're going to say, I want to put my building over that well, it's like, can't do that. So that has to come into and factor into that. So these, I talked about mostly vertical systems because of the land challenges here in the Northeast. In the Midwest, a farmer, if they have enough room, they could go ahead and just put 15-foot trenches and coil it as a means of getting more contact with the ground. And they have loose, silty sands out in the Midwest, and they could do it that way. And there are plenty of these systems out there. So here's an open loop system. Again, the same cartoon diagram of an office building, and it's showing an aquifer. Now, the people that developed this diagram, are Water Furnace. They're a supplier of heat pumps. And Water Furnace is not even aware of that rule of thumb I said, where when you take water out of the ground from one well, you need about 2 or 3 wells to put it back in the ground. So their cartoon sketch here just shows the mirror image of take it out of one well, put it in the other well. These open loop systems require a very, very trustworthy and great water quality aquifer. So we don't have those aquifers in the northern part of the state to speak of. We do in the southern part of the state, the coastal plain, and I'll show you a geologic map that speaks to that. And there are parts of eastern Long Island that have also very good water quality, where open loop is certainly a consideration. So here's another look at that standing column well, and these are again something that we're installing in New York City. They deliver for about a 1,500-foot well about 20 to 25 tons of cooling demand. And again, this is simply, it is a cartoon sketch, because when you design a well, you actually design it in a telescopic way where you start out drilling very large diameter bore on the order of 20 inches. And then by the time you get down to a depth of 1,500 or 2,000 feet, which is over a quarter mile into the earth, it's a pretty good feat to do that. You actually have to start drilling narrower diameter in order to advance a hole that deep. And again, what you have is, once this hole is drilled, and it's got to be drilled into rock, it's got to be good founding material. You have this casing, again, with a screen on the bottom. This is where the water comes in. You have a pump, usually about 250 feet below grade, and the water goes out to a heat pump, comes back, and then the water gets rejected and has all this time to get re-equilibrated. I will show you actual field pictures of the standing column systems. There's about 75 of them in New York City right now. And I will show you the standing column well systems.
I got a question for you. Where in New York City are you installing these? Because there's so much subterranean infrastructure in New York. I can't imagine where you guys are sticking.
You're absolutely right. So does everyone hear that question about where we're installing it and the subterranean challenges? I'll talk about that in our feasibility study. But in New York City, there's probably 15 to 20% of New York where you just cannot drill because of those subterranean challenges. So besides just what you understand as normal subterranean utilities, which are gas, water, sewer, New York also has the unique exception compared to most places of an enormous infrastructure of water tunnels, subways that are pretty extensive. We don't usually have that in most places, but New York is unique in that regard. And so, yes, you cannot drill a hole through the subway or drill a hole through a New York City water tunnel, although I would argue that that's a pretty good way to exchange heat, but I don't think the city would allow for that. So I talked about geology. So what you're seeing right there is, it's my son's rendering of New Jersey color by numbers. No, it's a geologic map of the state in a very simplified form. But what it shows is the northern part of the state, basically across here, is more or less shallow depth of rock and not great water-bearing materials. There are exceptions. There are valleys, and the rock in certain places has very good water-bearing characteristics. But more or less, in this part of the state, we all know there are extensive reservoir systems, and many of the populated regions are dependent on reservoirs because the groundwater is not capable of supplying water supply. All right, so the aquifers are not great, and there are exceptions. Lower part of the state, this is all one big sandbox, okay? And the sand is a great medium for obtaining water. So this is the coastal plain of New Jersey, and it's a great aquifer. We look at these from a perspective of where are you putting your system in, where are you building your building, and what are the geologic conditions. And this is just a very large map, and so we look at it even at a site-specific scale to really try to give us an understanding of the geology whenever we want to put these systems in. Not only is it important for the determination of what type of system, but it also comes into and factors into the cost of the system and the drilling costs as well. So again, I say that I talk to architects who are curious. They have a site, they want to know if they should look at geothermal, and we do a feasibility study. We try to make a determination, is it economically feasible and practical to put a system in at a given site where there's going to be a development. And I have this color-coded, so the first two are basically the realm of the mechanical engineers. The mechanical engineers have to determine what the heating and cooling loads are and whether or not they're balanced. So what do I mean by balance? That's a very important component of these geothermal systems. By balanced, I mean, is your heating load and your cooling load, are they about the same? If there's a drastic difference between the heating and the cooling load, you cannot use a geothermal system. So I'll give two obvious examples. If I want to put a geothermal system in to cool a hotel in South Florida, forget about it. That's all I'll be doing is trying to cool. I'm never really going to try to heat a hotel in South Florida. And all I'll be doing is rejecting heat into the ground. And after a while, instead of the average ground temperature beneath my hotel in South Florida being 72 degrees, which is the average temperature, and it's still pretty good to reject heat when you have 90 degrees out, eventually all I'm going to do is take that ground and heat it up. So It's not going to work in South Florida. It's probably not going to work in a nursing home in Maine or Alaska either. And you get what I'm talking about there. All I'm going to want to do is take heat out of the ground and very little cooling. So it's got to be in areas where the heating and the cooling is more or less equal. And if it's not equal, changes could be made to make it more balanced and supplement. Usually in this part of the world, even though it seems like we heat more, the cooling demand is more than the heating demand. And that's because we have things in the building that help heat the building that are just a coincidence. We all in this room heat this building. We have lights, we have mechanical things, and they all emit heat. And so there's usually a much greater cooling demand, even in a place where you might say, wow, today, I would think that they're heating, I mean. There are probably some buildings where you're not even aware they're actually still cooling. Okay, so cooling demand is usually greater, even where you may not think so. So it's up to an engineer to evaluate those types of loads. A cost analysis. So basically, the engineer is designing the systems and is most familiar with the systems. They would be able to compare a geothermal system to other conventional systems, to a high efficiency gas boiler, to an air to water exchange for cooling. And they will do a comparison and make a determination what the payback period would be for spending that extra money to drill holes in the ground and stuff like that. Where I would come in as a geologist is I would look at the geologic conditions to try to help the engineer on the cost side. What type of system are we likely to install, and what are the anticipated drilling conditions that will factor into the costs? Environmental conditions. In urban areas, you could drill a hole and you could encounter contamination that wasn't anticipated. While there may not be contamination on your property, someone across the street may have had a leaky underground storage tank for heating oil or something like that, and you might encounter contamination, and now you have to have an expense to deal with that. You brought up subsurface challenges, transportation and water tunnels. There's permitting requirements. Can you construct it? Can you actually get the equipment that you need to drill and install these wells on the property? And finally, what this really comes down to when you're looking at geothermal, typically in the Northeast, is do you have the footprint? Do you have the room outside of a given building to do all this drilling? All right, that's usually the first exercise. I look at this with my civil engineer colleagues, and we look at a site plan, we look at where an architect is proposing to put the building, and we make a determination, can we fit the ground portion of this system on our site? Yes or no? If it's no, we'll understand it in minutes. All right? So if I get a call from an architect and says, I have a client, we're putting up a building on 57th Street, and it's going to be 30 stories high, and we're occupying the entire site. I want to put a closed loop system in, I'd say, forget about it. It's not going to happen, because where are you going to put your system? You just don't have the room. Okay? So it's all about space. Groundwater quality considerations are very big. When you put these open loop systems in or standing column systems in, you're interacting with groundwater. And there are a lot of things that could factor in. When I put these geothermal wells in New York City, I'll show you a slide about, you know, the effects of salt water, corrosion, scaling, and also contamination. They come in really big on the two systems I talked about where we're pumping groundwater, which is the open loop and the standing column systems. Okay, hopefully I've talked about these systems enough. I'll show you some pictures and maybe you'll get a better idea of what they look like. This is at a site in Morristown, and the building behind the drill rig, that's what you're looking at, has a design, I believe, for a 60-ton system. We were putting about 2 dozen boreholes in that parking lot. The first thing we did was test to make a determination what the thermal conductivity of the ground was. So we're basically drilling a test bore and installing a test loop. And what you're looking at right there is a drill rig, just a conventional drill rig. This is a rollout, so you imagine you're drilling a hole into the ground, and as you're drilling a hole, you're pulling cuttings out of the ground, you're pulling parts of the earth out of the ground, and you need a place to put it, and it's just going into that rollout. But you can see it's a pretty big piece of equipment. Just a few more pictures of the operation. Okay, this is a pretty good shot, I think. So I mentioned the closed loop system is HDPE piping that goes in the ground. So right here you have that 6-inch hole. It's drilled right into the parking lot. And you have, I'll show you why you have 2 pieces of pipe coming out of the ground, but it's really one pipe. It's put together like a U at the bottom, and I'll show you a picture of that. So in this case, we have the pipe directly from the manufacturer, and we know we're going down to a distance of 350 feet. And in this case, that was a sand and gravel formation, and it sat on top of rock. And we decided to stop and not change over to drill through rock. So when the pipe went in the ground, this is what was at the bottom. Okay? So this is what I mean by a U-bend. So backing up, that part was in the bottom, and this just simply comes out of the top. So in what's here, this is basically a high silica thermally conductive grout. So it's a grout that sets up and has good advantages of exchanging heat. After that borehole is put in, we run a conventional test to evaluate the Earth's thermal conductivity. The test is pretty simple. This looks like a magic black box, but all it is a pump and a heat source. So we pump water at a constant and continuous rate for 48 hours, and you apply a constant heat source. And we watch and measure the temperature of the water in the pipe change over time. And that change in temperature is a function of the Earth's thermal conductivity. Once that thermal conductivity is understood for this specific location, then a mechanical engineer could model that and then design the system specific to this site. So I spoke about the open loops. I personally, as a geologist, I like to get more involved in the open loop systems. They're more challenging. They involve permitting. We're taking water out of the ground. There's usually a regulatory agency that wants to know, are you affecting other users of water? Are you affecting the environment when you take the water out of the ground? So I do what's called an aquifer pumping test. I assess the effects of that pumping of the water. We look at the water quality. We make a determination whether or not the water is compatible with the materials of the heating and cooling system. So is the water going to contact what in the heat pump when it exchanges? Is it nickel? Is it copper? Is it titanium? This all comes into play, so water quality is important. And then there's something called borehole drift analysis. So just remember that, and I'll show you a picture of what that means. So this is just a schematic of what an open loop system would be. You're basically seeing a cross-section of the earth, and you have a well that's in the ground. And again, think of a well as like a straw going into the ground with holes in the bottom. When you pump, you normally have a static water level. Groundwater is at this level here. When you pump, you're drawing that water level down. And this is for an open loop system. And then you're returning it into the ground. We have to evaluate and know this relationship of how much water is going to draw down and how much is going to mound up. We can't just go ahead and install these systems without having a very good idea in this example, what if the water was to mound up and start bubbling out of the ground? That would not be good. Or what if as we pumped, we drew the water below the pump intake? Also, that wouldn't be practical. So there's a lot goes into these open loop systems. And this is basically showing the same effect of the groundwater, but in a plane potentiometric view where you have contours representing changes in water level. What I'm trying to get at here, the simple takeaway is we don't want the extraction well to be hydrologically affecting the diffusion well. We want them separated so that you're not creating basically a short circuit. So wherever you pull water out of the ground, wherever you put it back in the ground, you want them to be hydrologically apart and not affecting each other. So I'm going to end up with the standing column well, and these are wells we've done in New York City. And basically, this is a site on Park Avenue. And I mentioned way in the beginning that it's all about the economics of it. There are certain times where the economics don't come into play. There are certain times where an individual owner, they want to bring cooling into a building that might not otherwise have had it. And the building may have some significance. In this case, it's a building on Park Avenue that is basically protected architecturally, all right? So it's historically preserved. There's rules and regulations that do not allow someone to change the facade of the building in New York City. So you have an owner who purchased a very expensive duplex apartment in a building that has historical significance, and that owner cannot just put an air conditioning system in the window, okay? That wouldn't fly. They can't put anything on the roof. They cannot change the facade at all. And so they asked their architect to come up with a creative way to allow them to cool their modern apartment. In New York City, this building was probably built at the turn of the century in a way that could make them feel comfortable. And so in this instance, it was very expensive. And there's no payback. There's no efficiency for the owner. But it is a way for a wealthy person to gain comfort in a building that is otherwise protected and there's no options for them. So that's what this is about. I keep on using this advancer. So this is just an example of, imagine pulling all this together in New York City. And New York City, you need a permit for just about everything. A permit to close the road, to close the sidewalk, to put each piece of equipment on the sidewalk. Here's where the cuttings are coming out, okay? We have this, I'll explain this, but this is basically, there's a screen in here that allows the rock cuttings to settle on top of the screen, and then the water is routed through this hose into a New York City sewer, again under permit. You could imagine we have these barriers in place, and we even needed a permit from the Parks Department to trim back one of their trees.
How much that one cost?
This is probably, I call it the $400,000 air conditioner. Yeah. So this is unique. It's not every day that someone has $400,000 to shell out on an air conditioning system, but there are sometimes those that happen. What's up?
For the standing column wells, when they're at a depth of 1,500 feet, how long does it take to drill something like that?
Generally, the drilling portion, if there are no problems, and there was always problems, but 2 to 3 weeks. 2 to 3 weeks, but the entire system may take double that.
Okay.
Okay. Yes?
For this process that's going on, when they're putting the standard column wells, they're doing it for one duplex, or for the standing column well, is it going to produce more heat, more cooling than that duplex could ever need, or are these column wells and other things proportionate to what they're going to keep cooling or heating?
Yeah, it's a very good question. So in this instance, the duplex needed about 12 tons of cooling load or the heating equivalent. And these wells are generally capable of about 20 to 25. So there was excess. And it was only being put in the ground for one individual. That individual had to petition and get the, when you get a permit to close a sidewalk like that, you're also seeking what's called a permit from the city of New York to build something that's yours privately on city property, okay? So the city doesn't usually do that very often. They don't like to, unless there's an overall good. In this instance, you could say, well, what's the overall good? Well, this is one person who's saying, I am going to be heating, I'm going to be cooling, and not for nothing, it's a green technology, and the city allows it. It's not often that the city allows you to use their sidewalk. Certain instances, you know, restaurants maybe apply and get permits to use sidewalks, and they look at that as just a neighborhood good, but it's not typical of being able to just put a well on someone else's property, which is what this individual did. They put it on New York City property. Now, we couldn't have heated and cooled the whole building this way. There would not have been enough frontage to the building to put in enough to do everyone's apartment.
So for this one duplex, since they're going to have extra energy, where is the extra energy go? Where does it just stay in the system until they use it? Like,
It's not extra energy. Again, all you're doing is you're relying on the earth to reject heat or to draw heat, and there's no energy involved. So you're basically, you have the capacity in that hole to reject or draw more heat than you need to. That's all you have is more capacity to do it if you needed it, but all they need is about half of what that hole could give them. All right? This here, this is unique. You didn't see it in the other picture, and that is you're drilling now down a quarter mile almost into the earth, and you're picking up pieces of rock out of the ground. And in order to do that, the medium that you're lifting the rock up with is air and water. And you could imagine the amount of forces you need and the velocity to bring pieces and particles of rock out of the ground. Now the rock is pulverized. That's what the drilling equipment does. It's pneumatic, and it's basically like a hammer. So air is being delivered to work a tool that has diamond bits at the end that's hammering the ground, and then the air, through enormous delivery of air, is bringing these cuttings up. And it's going into here, which is almost like a muffler, if you will. It's basically reducing the energy that the cuttings are being lifted with. And they drop out into this conventional roll-off. And again, the roll-off has a screen at the bottom and allows the cuttings to get trapped on top and the water to get delivered to the sewer. And then typically in this case, about once every other day at about 4 in the morning, we'd have a contractor come in and roll this off and take it away. Dump the cuttings.
You did air rotary instead of mud rotary, right?
Absolutely. So the question was about the technology used to drill. And when we drill in rock, we use what's called air rotary, which is what I explained. It's a pneumatic, it's a hammer in the ground. It's almost like a jackhammer beneath the ground. So this is what the drill rig was maybe on the site for 2 to 3 weeks. We did this in the last week in August. When you do projects like this, there's all these constraints, and the building basically says we have a window to build or do renovations. In this building, it was a very narrow window from like the middle of June to the first week in September. And this is a very wealthy clientele type building, and they allow summer construction because, quite frankly, they're all at their Hamptons house or somewhere not in their building. So they tolerate summer construction because many of them are not in their building in the summer. So I talked about drift analysis. So the state of New York gives us a permit to drill this deep well, anything over 500 feet. But when they give you that permit, one of the conditions is you have to monitor where that borehole ends up. And when you drill a hole, it's not a given that you're going to get a perfectly plumb straight hole. The borehole does wander based on differences in the strength of the rock and how that bit advances. So it's not unusual for a 1,500-foot hole to start at one location and wander 50 feet. And the state of New York does not want to be conditioned to a trespass. And while it sounds crazy and impractical, they do not want to allow you to trespass underneath someone else's property, even though what would that mean from a practical perspective if you found out that there was a hole beneath your site, beneath your property that's at 1,500 feet? It's not going to affect you in any way, shape, or form, but it's a legality. And so this is a geophysical contractor who's setting up and he's monitoring the actual drift of our borehole. This is what the well looks like when it's ended. It's just basically a New York City manhole. If you pull the manhole up before it was backfilled, you have a water line going in, a water line coming back, going into the building, taking water back into the well, and just electrical conduit. This all gets filled up with sand, and if you lifted the manhole, all you'd really see is this, and if you lifted this off, that would give you access to the pump. So that's what goes into the building, and in this instance, the owner was able to put their heat pump in a storage room in the basement, so it didn't affect the architectural integrity or significance of the building whatsoever. I'll go over, how are we on timing? I have another quick case study for Columbia. Are we good?
I think the next one's at 12:30.
So we're good?
It's 5 to 12.
5 to 12? I go through this in about 5 minutes. Stay within the hour. So this is Columbia University. It's a building on 122nd Street. This Clarendon is about the equivalent of 11th Avenue, and Broadway's at the end here. So it's on the west side, not that far from the Hudson River. This standing column well, we put 4 of them on the sidewalk to heat and cool the entire building. And across the street was the New York City School of Music. And in the summertime, they did have people practicing, and they didn't want a lot of noise coming out of our drilling equipment. So you had the sound barrier. I think this is up about 25 feet or so, sorry. And is everything okay?
Yeah. I just see it.
Is that better? And this is the drill equipment behind it. So again, this is just another standing column well. When we put these wells in, we do what's called an aquifer pumping test. This is just a driller who's getting ready to set a pump in a well. So there's a pump set up, and we ran a test. And what we did is we pumped the water in the well at different rates. In this instance, we went from 5 to 10 gallons a minute, and we monitored the water level in the ground as a function of our pumping. So basically on the x-axis, you have time in minutes, and this is a semi-logarithmic plot. And on the y-axis, you have drawdown, which is basically the difference between what your static water level is before you start pumping and the water level during pumping, because you're drawing water level down. That's called drawdown. And what we do is then project that out on a time plot, for a period of 6 months. And we try to make predictions about what the ground is capable of giving us while we're pumping. Typically, it's a direct circulation, so we're not concerned. These wells are meant to pump at about 100 gallons a minute, and they circulate water in and out of the well. So there's no net loss or gain to the ground, and you're not that concerned from a hydrologic perspective. But during periods of peak demand, so those couple of weeks in July when it's 95 degrees out for a week or two straight, these systems get more efficient if, as you pump water out of the ground, you reject some water. And the ground's got to make up that water, and make up that water hopefully at the ambient temperature of the earth. And you have to design your system to be able to reject that water, and that's what this pump test does. We also do water quality analyses while we're pumping, and we had 4 wells, and here you can see changes in the water chemistry. So well 1 is closest to the Hudson River, and look at the total dissolved solids, and look at the amount of calcium in the well and the chlorides in the well. They're about an order of magnitude greater than well 4, which is along Broadway. And we have to take that chemistry into effect, and we did during our design. And we designed this system in an iterative manner. And so what we learned during this design is that the well didn't, the well we originally expected to be able to reject about 10 gallons a minute. And through the plots that I showed you before, I didn't get into it, but we learned that we were only capable of about 5 to 7 gallons a minute. So we wound up drilling from 1,500 feet down to 1,800 feet to make up for the inefficiency of the well. And then we also learned that the water quality was pretty bad. It was had a lot of minerals in it, making for potential fouling with some of the components of the system. So we had the building piping for the heating and cooling system modified to go from steel to PVC, which is a big deal in New York. New York has old fire code regulation that requires you have metal pipe. So we had to get a variance from the city building department to go to plastic. And then our heat pump was modified to incorporate titanium into the heat exchanger, so something that would resist any kind of corrosion, making it more expensive, but again, in the long run, perhaps better because less O&M. So that's it. That's my talk. There's a lot out there on geothermal. This is something for owners. There's tax incentives from the federal government, but if anyone has any questions on these systems.
Brian, I just want to, you brought this up before about New Jersey, Pennsylvania being the prime, and I think we got to remind people here that this is for low temperature, while high temperature, say if you go to California or Alaska, you might be able to make electricity and use geothermal at the high temperature level in a much different way than what you've been talking about. So that's something, you know, when people think of geothermal now, I hope that they realize there's 2 different types.
Right.
Yeah.
So the point is, I tried to make this earlier on, there's what's called a high temperature geothermal system and a low temperature. What I've just given you is a low temperature system, which is basically using the earth to exchange heat. That's all that's being done. The high temperature systems are those that you think about in like Iceland, where there's volcanic activity and they could drill a hole and they can get water that's almost at a temperature of boiling. You know, they can pull water out of the ground at 150 degrees, and it doesn't take much to heat that water up for boiling, and then boiling they could use for steam generation to run a turbine, and they generate electricity with that. So those are 2 completely different things. One is for the generation of energy, and the other is only for a medium to exchange heat. So I wanted to make that clear that we're talking about these systems for heating and cooling is only to exchange heat. Those are low temperature, and they're in geologically stable areas like we are here in New Jersey, Pennsylvania, and New York. There was a question?
For the heating capacity, you were saying it was measured in tons. I missed that before. And what is it measured in tons of? Is it?
Okay, so it's tons again. It's almost the equivalent of. We're all familiar with horsepower, right? So it's just an old British standard of measurement. It comes from the amount of cooling derived from a 1-ton block of ice melting. So it's just a. Tons is also converted to BTUs. So I believe off the top of my head, it's like 1 ton is something like 1,200 BTUs. So that's another standard of system that's used for measuring these systems. So, all right. Yeah.
When you install these, are they the sole heating and cooling system in the building, or are they often supplemented with your boilers or?
Yeah, so they can be, and certainly on a smaller scale they are. On the larger scale, depending on what I talked about was the balance. So let's say if you have a system where you might have a cooling demand of 200 tons and a heating demand of 150 tons, you want to design the system for the lesser load so that you balance the load. And so then what would happen is you need a 50-ton makeup system for cooling. So in that instance, it would be a hybrid, and you'd have the bulk of your system would be for heating and cooling using geothermal, but during the peak periods, you may have to supplement your cooling load. Now the thing is with these geothermal systems is a lot of times, and this is where the engineers come in, when anything is designed, it's designed to take into account the worst case. So when they design this building and they design the cooling for this building or for the university, they don't design it for a day in May or a day in October. They design it for the worst case. The worst case is we may get how many days in July that's 95 degrees and 95% humidity. Now maybe they say, well, okay, July, it's a university, there aren't that many students. So maybe a June day would be more of a cooling load where there's still students around and it's still hot. But those are how these systems get designed. They get designed for the worst case. Now a lot of times the geothermal, it may not be practical to design the geothermal to the worst case. You design it to what you need for 80–90% of your time, and then the engineers that design the system could say, I need 10% of my time, I need greater than what the geothermal is providing, and I'll augment that through other means or other systems. And it might be economical to do it that way. Any other questions? Well, thank you for having me. I hope you got something out of this and try to learn a little about these systems.